Power is the rate at which we do work. In general, it is energy, is our change in energy. Actually, not change in energy, change in work. Actual work. Okay, which equals the change in our kinetic energy divided by our change in time. This would lead us to a joule per second is our unit. Okay, and this becomes a watt. Okay, not to be confused with, or we abbreviate that as a W, but that is not to be confused with work. So make sure you keep these straight. That if there's a number in front of this, that means we're talking about power and we're talking about number of watts. If we, if it's just if we're dealing with just variables, then it's work. Joule per second is a watt. Okay, is 1 joule per second equals 1 watt. Okay, there are other and from this, there are other ways to think about it, to relate this to what you guys have seen before. You may have heard of kilowatt hours. Okay, a kilowatt hour is an amount of energy, amount of power times time, and this is equal to, that's equal to the amount of work, because if we have this over here, if our work divided by our time equals our power, that should be equals power. If our power equals our work divided by our time, then our power times our time is going to equal our work. And so this kilowatt hours is a version of the amount of work done, or just the amount of energy used, because it takes energy to run appliances in the house, and this is usually our measure of electricity, is in kilowatt hours. Now, I don't understand why we don't just use joules, but I think people, well, it's sort of an artifact of how we rate our electricity. Other thing about, there's another version of power, and it's horsepower. Okay, and you'll hear, you'll hear like cars are rated in horsepower, but that's really just, they are measuring power, and it's just another form of watts. And we're going to do a real quick search here, because I don't remember what it is. So, Siri, how many watts is 1 horsepower? There you go. 1 horsepower converts to 746 watts. So 1 horsepower equals 746 watts. Now, the way you can relate this to cars and stuff, okay, or engines, where we usually hear horsepower, you can have cars that get a lot of energy. So in other words, my Honda Element, okay, I can go pretty darn fast in my Honda Element. It is not the most powerful vehicle, but it can get up there. In fact, it's high end. Its power at the high end of its tech is better than the power at its low end. But what you can do from there, once you're already traveling with a certain amount of energy, what you can do, the rate at which you get up to a particular speed, is not acceleration. Okay, it's more the rate at which you can accelerate is closer to power. Is a real world way of thinking about power. It's how much energy can your car put out per unit time. So if it can increase its energy faster, it's going to have more power. You follow? Okay. Another example would be like semi-trucks or trains or really large vehicles, buses. Okay, buses have huge engines, like our school buses that we ride on. Huge engines. Okay, it's just because they're big vehicles and they have a lot of people on them, and so they have to be able to move a large mass and get them up to speed. That requires in a reasonable amount of time. Now you could put this on a really slow vehicle and it could eventually gain that energy, but that means the power isn't going to be there. Because remember, it's our change in power over change in time. But if we increase the mass, okay, then it requires a large engine in order to change its energy in a reasonable amount of time. Yeah? You guys with on that? Okay. So there's another version of power. Or not another version of, but another way of calculating it. It also equals the force you can apply on an object when it's already going at a certain speed. Force times velocity. Okay. So this is another way of relating. If you're already traveling really fast, how much force can you apply to something that's already traveling quickly? So you look at you're going 100 kilometers per hour, and you want to accelerate to 130 kilometers per hour. The amount of time it takes to do that, okay, is going to depend on how quickly you can accelerate. So if your acceleration, right, if you can exert a force at this 100 kilometers per hour, okay, the greater force that your thing can apply, traveling at this speed, is also a measure of the power. So, and just for argument's sake, a joule here, this joule per second, equals a kilogram times the meter squared per second squared is our joule. Divide that by a second, and it equals a watt, which equals a kilogram meter squared per second cubed is the actual unit for a watt. Down here we have force. Force is a Newton times our velocity, which is meters per second. A Newton is a kilogram meter per second squared times a meter per second is also going to give us a kilogram meter squared per second cubed. And these two are the same thing.
What's before the M?
What's that?
Before the meters per second.
Here?
Cube. Yeah.
Kilogram.
Oh.
Okay, so there you are. Okay, so real quick. Here's your work. What's that? Right here? That's a 3, yeah. It's a cube, so it's s cubed. Okay. Okay. These front page should be able to answer. What have we done so far? Well, we worked in power calculation, so I'm going to work through the first one for you guys, and then we'll move on. So Bart runs up a 2.91 meter high flight of stairs at a constant speed of 2.15 seconds. If his mass is 65.9 kilograms, determine the work which he did and his power rating. Okay, there are two ways that you can do this. you can find his velocity and then multiply it by the force that he would need to climb upstairs, because it would be, his acceleration would be due to gravity. Okay. Or you can find, okay, so the second one, method 2, so let's do method 1 here. If you connect these two, okay, to give you velocity, or number 2 to go with energy. Okay, so I'm actually going to do number 2 first. We're going to do energy. So this is going to be 65.9 kilograms, and he runs up 2.91 meter flight of stairs. So he's going to increase his potential energy. It's going to equal 65.9 kilograms, right? Because equals mgh. All right. Times 10 meters per second squared. Times the height is 2.91 meters. And that's going to equal that's going to equal 65.9 times 10 times 2.91 equals 1918.
What do you stand for?
Potential energy. It's what I use in my other physics class, and I've always learned it as U, so it's just habit to do U. Okay. So that's 1918 joules, and then power equals our change in energy over change in time, or our work. Our work done divided by time, which is going to equal 1918 divided by our time was 2.15 seconds. And that's 892 joules. I'm sorry, watts. Okay, that's method 2. That's going the energy route. We can go a different route where we can find our power equals our force times our velocity. Okay, and that would be our force is going to equal mass times gravity, and our velocity equals our height divided by our time. So it's the distance divided by time. Okay, but you can kind of look at this, and it's going to be the same thing. mgh divided by time. This is going to be mg times h divided by time. So this will also equal 65.9 kilograms times 10 meters per second squared. That's our force. Okay, times our velocity, which is 2.91 meters over 2.15 seconds. And you can see how these two things are going to wind up being the same as what we did over here. 892 watts. You don't have to do it both ways, but you can choose either one.
So you did two different ways to.
Two different ways to do the same thing. It's either change in energy divided by your change in energy divided by your time, the rate at which you change your energy, or it's your force times your velocity that you're traveling. Okay? Those are the two things. 2, 3, and 4 are up to you guys on this page, as well as all the concept questions on the page before. And that's it for today.